Okay, so we're going to continue confidence interval discussion, and if you have started to read in section 7.2 in your book, there is another kind of confidence interval we're going to talk about. So the ones that we learned about in the last section were for, so 7.1, let's see if I can get my marker to work here. 7.1 was for samples, right, of size n greater than or equal to 30, right? Or if we knew the population was normally distributed. Okay, so that was the first thing. And I think the other kind of condition your book now talks about is you know what sigma is. So it's either, if you're in one of those two categories, you use 7.1. In 7.2, we now talk about things, right, where sort of n is less than 30. And how do we calculate confidence intervals for that? And so if n is less than or equal to 30, then you know that there's no central limit theorem that actually applies, right, to this particular situation. So we actually have to use something other than the z. So as we start to calculate our x bar plus or minus e, right, that sort of e thing, it's going to look only slightly different. And the formula that we're going to use is x bar plus or minus t alpha over 2 s over the square root of n. And also we have to know this little thing, and I'm just going to write it here for right now, and we'll talk about what it means. df is going to equal n minus 1. That's the degrees of freedom. So this is the formula. The only thing that you'll really notice that are different between this and what we did in 7.1 is that this is a t instead of a z, and we're going to be using the s because we're going to assume that we don't have any idea what this population standard deviation is. So otherwise, though, it's the exact same sort of process that we did in the last section. Okay, so let's go through and talk first about how to do this t business and what this t is, and then we'll do an example so we can see. So the t distribution we use, all right, so here's our sort of standard line. We have a 0, and this, let's say, is our normal distribution, right, centered at 0, so this is our normal distribution. The idea here is that with a t distribution, it's called the student's t distribution, and it varies based on the size of your sample. And so there are t distributions with different degrees of freedom, and the degrees of freedom are based on your size of n. So it's often abbreviated df, and that is going to equal n minus 1. And we subtract 1, just kind of like we do with the standard deviation formula that we learned at the very beginning of the semester. We just take away 1 to account for some statistical sort of errors that we have to do. All right, so we're talking about student t distributions, and it varies based on n. So this is our normal distribution, and the student t distribution looks almost identical to this, but what happens is that we get a little bit more area at the sort of tail. So sort of down here, we're going to get more area and a little bit less in the middle. And the closer that n gets to the original, right, the closer it's going to be the actual normal distribution. So for all intents and purposes in this class, once n is at least 30, we're going to pretty much say the student t distribution is almost exactly the normal distribution. And if t is less than 30, we will look at different distributions. So for example, we could draw one that maybe looks something like this. And that maybe is a t distribution, let's say, with, I don't know, let's say 12 degrees of freedom or something. Okay, because it's pretty close to the normal distribution, right, but it's a little bit different. And then we could draw another one, right, where this is going to get even fatter out here, right, it's going to get even shorter there in the middle, right, because the area still has to be 1 underneath. And maybe that's with, I don't know, 6 degrees of freedom. So this is not the best drawing. There's a much better drawing in your book if you kind of want to get an idea. But the main idea is that the student t distribution is still centered at 0. It's just a little bit fatter on the ends. And so when we start to calculate that sort of t of alpha over 2 business, the first thing you have to decide is, what is my degrees of freedom? Okay, so because you have to decide that before you can actually decide which t distribution you use, because there are all kinds of different t distributions based on your degrees of freedom. And then once you decide that, then you're doing that same question, right? You're looking up, find alpha over 2, right? just like we did with z of alpha over 2, you need to calculate what that is. And then there's this interesting table that I'll kind of talk about here, and if you want to look in your online, you might want to take a moment to pause the video and go see what the t-distribution table looks like. I'll kind of draw a picture of it on the next page. But then when you go to that to calculate, right, you're still calculating t alpha over 2. It's just like you calculated the z, right? It's that sort of idea that the area over here plus the area over here, right, is equal to that little thing you're trying to calculate. So we're still doing the same thing like we did with z, we're just using a slightly different distribution because of the fact that we don't know, it's not exactly normal. It's close to normal, but it's going to be a little bit skewed, and that's what the student t-distribution will do for us. Okay, so let's look at a t-distribution table, and let's say we were trying to calculate if we wanted to do a 95% confidence level for n equals, I don't know, 5. Okay, so if we were trying to do a 95% confidence interval for t equals 5, we would get that t alpha over 2, right, is equal to what? That's what we need to figure out. So alpha, remember, is 100 minus 95, right, which is 5. And then if you want to convert that to percent, these are percents, right? This is percent, which is really 0.05. And then alpha divided by 2 would therefore be 0.025. Okay, so that's our alpha divided by 2. So we're going to go to our t-distribution table. So check that out. It's in the back of your book in the supplements in section 12. And there's actually an entire page. I think it's looks like figure 12.3. So figure 12.3, if you look at this table, along the side it's going to have your degrees of freedom, right? It's going to have 1, 2, 3, 4, and so on. And then across the top, it's going to have your t sub whatever, 0.2, I think, and then t.1, and then t of 0.05, and then the next one I think is t of 0.025, it is. So, for us, right, and then there's all these numbers kind of down in this sort of section here. There's like all kinds of numbers in this section. And your goal is really just to find, right, those t values. And then that's all you have to find. You don't have to do any subtraction. You don't have to do anything crazy like you do with the z-table. This is a table of those t values that you need for confidence intervals. So you don't have to do anything else. You're just getting the t. It kind of works a little bit differently than the z-table. So if you look here, right, we have all these things. And so for us, right, our degrees of freedom in this case, n is equal to 5. So our degrees of freedom is going to be 5 minus 1, which is going to be 4. So we're going to go along this line, right, until we get t of 0.025, and we want to take the number that's right there. So if I look at my table, I'm going to get 2.776 is what I see in my book. So 2.776 is what I would use there. And that would be my t of alpha over 2. Okay, that comes straight from that table. Take the 4 line. Remember, degrees of freedom is 1 minus n minus 1. So 5 minus 1 is 4. You scroll all the way across to the t of 0.025, and I see 2.776. And that's the number you use for t of alpha over 2 if you were doing a 95% confidence interval with n equal to 5. So now we'll try an actual example, and I believe this example will also be helpful for other homework problems that you have, even from 7.1. And it's interesting because in this problem they don't actually give you the mean or the standard deviation. You actually have to calculate those based on some data that's given. So I wanted to do one like that so you can recall how to do those kinds of things. So this is going to be number 17 from section 7.2 if you want to find that in your book. Okay, so number 17 in section 7.2 says that botanists studying attrition among saplings in new growth areas of forest diligently counted stems in 6 plots in 5-year new growth areas, obtaining the following counts of stems per acre. There were 6 counts, so 9,432 stems per acre, 8,773, 11,026, 9,868, And last but not least, or no, I guess there are two more, 10,539 and 10,247. So these were the 6 sample data points they got for the samples that they collected on the forest. And they want you to construct an 80% confidence interval for the mean number of stems per acre in all 5-year-old new growth areas of forest. And we want to assume that the number of stems per acre is normally distributed. Okay, so it's asking us to calculate this 80% confidence interval for these 6 things related to number of stems per acre. So if you think about your formula again, right, it's x bar plus or minus t of alpha over 2 s over the square root of n. Now, in our problem right now, it's pretty clear, I hope, that n is equal to 6, right? There are exactly 6 data points for this problem, so we can count that and get n. We don't know s, and we don't know x bar because those are not given to us in the problem. We're going to have to calculate those using the formulas we learned at the very beginning of the semester. So I'm going to save that. I'm going to go ahead and do the t of alpha over 2 because that's how we just talked about in the last section about how to find that. So we need to first, to do t of alpha over 2, right? First we need to figure out what alpha is. Alpha will be 1 minus 0.8, right, which is 0.2. So alpha over 2 is going to be 0.1. Okay, so that's your first step, is finding alpha. Now we need to find degrees of freedom. So remember, degrees of freedom is n minus 1, which for us is going to be 6 minus 1, which is 5. And now we use the table. So look at your table, right? You're looking for, along here you're going to look for a 5, and up here you're going to look for t sub 0.1. And you want to find where those two intersect in order to get your t of 0.1. Now I looked that up in my table. It looks like I got 1.476. And that's the number that we'll use as our t of alpha over 2. So we now have t and we have n, but we have to get x bar and we have to get s. And those are 2 formulas. X bar you probably remember how to do, but you may not remember how to do s. So we'll go back through that formula one more time on the next page. Okay, so x bar, right? Hopefully we all remember how to do that. That's just the sample mean, right? That's just adding up all these numbers, 9432 plus 8773 plus, right, I'm going to put a dot, dot, dot here, but hopefully you recognize that you have to add all 6 of the numbers up, right? And then you divide that by 6. Okay, that's going to get you your sample mean. There are 6 values. You add them all up, divide by 6. I got 9,980.83. So that's my x bar. Okay, so that's the easy calculation. So now's the one now nobody remembers, which is standard deviation, right? Sample standard deviation. Remember, it's a square root. You take the sum of all your x squareds and then subtract 1 over n, the sum of your x's squared, and then you divide that by n minus 1. So that's that fancy formula that nobody remembers, but it's one that we'll need in order to calculate sample standard deviation. So the sum of the x's, right, that's actually the same value, right? This is the same as this number that you'll get up here, right? Those two numbers should be the exact same. So that is no different. That's not a new calculation. But for the sum of the x squares, right, let's go down here and do that calculation really quickly. So for the sum of the x squares, remember what you have to do is take 9432, square it, add 8773, square it, right, and keep doing that all the way down to 1024.7 and square it. Right, so you'll add all those up. So for me, that squared number, I got 600,949,783. Okay, so I now know what my sum of my x squares is. The sum of the x's, this guy right here, remember, is the same as this sum on the top of your x bar number, and I checked that out and I got 59885. So the sum of the x's is 59885. And remember, you're going to just square that to get the number that you'll subtract. So you'll just subtract that's 59885 squared. Okay. Okay. So on the next page, we'll do that whole calculation and get S. So here we go. So S is going to be the square root of 600, 949, 783 minus 1 over 6 times 59885 squared. And then remember, you divide by n minus 1, which is 5, or 6 minus 1. You type all that into the calculator really careful. I got 805.925. Okay. So I believe we now have everything we need in order to calculate our confidence interval. X bar plus or minus T alpha over 2 S over the square root of n. Okay, so X bar, you can go back a couple of slides. I don't know if I can do that in the middle of my talk here, but X bar, let me see. I guess I can't. So just go back and kind of look at that previous slide if you want. But remember, we calculated it. X bar was 9,980.83. And then we plus or minus, we also calculated T of alpha over 2 a couple of slides ago, and that was 1.476. We now have an S of 805.925, and we divide that by the square root of 6. And that's all that you need in order to calculate it. So you do that one at a time, and it looks like you're going to get about, if you go kind of carefully and add all these things up. Okay, so if we do all this addition, I'm just going to go ahead and round off some of the decimals a little bit, but you can do it, right? You can get some decimals. It just makes the subtraction easier for me. You're going to get about 9495 on the left, and you're going to get about 10467 on the right. All right, and so that'll be an 80% confidence interval for the sample means of the number of stems per acre in these forests. Okay, I'm sorry, not for the sample mean. Oh, let's erase that. 80% confidence interval for the population mean number. The population mean stems per acre. Okay, so remember, it's a confidence interval for the population mean, not the sample mean. That's important. So the big takeaways from this, right, make sure you understand where this number comes from, right? That's only the big new thing here. This is old. I just wanted to go through one more time to show you how to calculate that S. Majority of the problems you're going to be given that S, so you don't even have to take the time to calculate it, but I just wanted to show you, in case you do have some problems that you have to calculate that, how to do that one more time. But in general, the only new thing in this section is thinking about T and how to use that table. We'll look in class a little bit more how to use that table just to make sure you understand, but that's the only new thing.